first half of D is double in size. Okay.
Fine. I am just following intuition right now, but I think that it's not possible that division will work.
First half is doubled in size, the distribution changes, so it's likely to change. That's it. Okay. Any other questions? So everybody is apparently all up and up about things. Okay. This stuff, child's play, right? Okay. Any questions on this? Okay. So I am basically going to go forward on. We were talking last class about this whole notion of low-rank approximation. Well, I didn't use that word, but this is the technical area, low-rank approximations of matrices. Okay, and in essence, what we did was previous to this. So previous to this, we talked about the fish, and we talked about trying to reduce the dimensionality by looking for axes that capture the maximum variance, the next maximum variance, and so on. And went from fish to, and we also noticed that, in fact, when you do this, in essence, you are kind of putting an ellipsoid around the data. It can be an n-dimensional ellipsoid, and then you can compute the eigenvectors and the eigenvalues, and then essentially, so in this case, it's a two-dimensional situation, and so you have a primary eigenvector here, a secondary eigenvector here, and the primary eigenvector would be your primary direction, so that's the one that captures the maximum variance, and the one that's orthogonal. All eigenvectors are orthogonal to each other. That's the whole point of eigenvectors. Okay, so in 2 dimensions, there can only be 2 of them, obviously. And so then the secondary eigenvector captures the remaining amount of variance. And furthermore, we can also actually talk about, we mentioned that we can talk about the notion of how much of the variance is captured by, how much of variance is lost when you, for example, remove some of the lower variance dimensions. And to do that, you essentially take, in this case, you take the fraction of, so if you are lambda 1 up to lambda I, you are keeping, and of which lambda I up to lambda n are the total number of eigenvalues, then you add the ones you keep, divided by, that doesn't work unfortunately, I'm sorry. So, especially today because I'm going to write a lot on the board. Divided by the sum of all the eigenvalues. Okay, and that will give you the amount of variance you are able to capture, and 1 minus that will give you the variance you are not capturing. Okay, so that's something that we talked about, and we will find some similar way of doing things for the SVD also. So anyway, this is basically called principal components analysis. You don't need to know the name. But we wanted to see if we can do this for fish. Can we also do this for the documents? And then basically said, yeah, you can do it. Essentially compute the SVD, the singular value decomposition of the document term matrix. And then basically the singular value decomposition of the document term matrix would be of the following form. DT is written as, is decomposed into 3 matrices, DF times FF times DF prime. Okay, so if DT is, let's say, a 10 by 100, okay, 100 documents and 10 terms, right? Then that would be decomposed into, so this is D times T. This guy's size is D times T, and this would be decomposed into the following matrices: DF, which will of course have 100 here, okay, and for now we'll have 10 here, Okay, and then FF, which would be a 10 by 10 diagonal matrix. Okay. Actually, no. Let's just think about. Let's not. It's size F. Let's just assume that's a size F, and this is size F by F for now because we keep changing. And then this last matrix is TF matrix. So think of this as here. This matrix is telling you documents written in terms of the space of terms. This one is telling you documents written in the space of factors, which is some sort of a latent dimension that we are finding. Remember, the reason you need latent dimensions is this is a factor now. This thing, we gave it a name called size, but it's, you don't necessarily have a name. If I put an arbitrary vector in this space, it might not have a name. So these are the variables that we think, these are the directions that we think we should be focusing on, and so those are the latent factors in essence. Okay, so that's where the word latent in latent semantic indexing comes in. So you are given certain set of dimensions. Those are the ones that you look at in the documents and terms. The terms are the dimensions for the documents. But you are essentially arguing to yourself that maybe terms are just what you see on the top. What really matters is these latent factors. It turns out that both documents and terms are vectors in the space of factors. Okay? You'll see enough examples, don't worry about this for now. Okay, so then you have this F by F, and then this one, TF prime, so you will essentially have F and T. So this would definitely be 10. Right? Okay, so it's TF prime. So normal TF would be, T would be rows and F would be the columns. Okay, so there would be, so find a decomposition of any matrix such that this, and so you have three matrices whose multiplication becomes this. Okay, now what's interesting about this is the following. How do I get this? The way to define SVD is that PF, this guy, this is nothing but the eigenvectors of DD. Now, where is DD? I'm using these terms. I know most of you, in fact, somebody even went onto the web and found SVD and copied it onto the tweet notes. Basically, normally when people talk in terms of SVD, they use UV as the matrices. Okay, but I actually have a good reason to use this because this way you'll never get confused as to which document is supposed to stand for what. The DT document is document in the space of terms. Okay, the DD document is a document-document correlation matrix. How do I get a DD matrix? DT times DD, right? So the DD is nothing but DT times DT prime. Right? So you know how to do this. Okay? So if you have a matrix thing like in a MATLAB or something, if I give you a big matrix here, you can compute the DD. Now what's interesting about DD? Notice that this is, you have done eigenvectors before. Right? I mean, when you're in linear algebra. Eigenvectors are defined for square matrices. This one, it doesn't have to be square. This one is 100 by 10. In fact, normally document by term matrix would be some rectangular matrix. It doesn't have to be square matrix at all. So SVD is actually a generalization of the same sort of concept for rectangular matrices. Except here's the interesting thing. DD, what's DD? It's a square matrix. Furthermore, DD has a very interesting property. DD is going to have, it's what's basically a symmetric positive matrix. Okay? So because in the DD, the term Aij and the term Aji would have to be the same. Because that's the correlation of document 1 to document 2, document 2 to document 1. Okay? So it turns out that in the theory, so I got DD. Now this is a square matrix, so you can compute the eigenvectors for square matrices. Right? So df is nothing but the eigenvectors of the square matrix dd. That's it. Okay? Now what about df dash? It turns out df is eigenvectors of tt. Now tt is nothing but tt is nothing but dt prime times dt. That's the term-term correlation matrix. Given a document term matrix, you can compute both the term-term and the document-document correlation matrices. Those are sort of squares of the original matrix. Because it's rectangular, one square corresponds to the document square, another square corresponds to the term square. Yes?
So in the dt is in the first, for df, the second one has the tick, and the gt, the first one.
I didn't get your question.
So they're switched?
No, you're saying, why am I doing df dash here? Because that way, df times ff times ft would again be dt. The inner dimensions have to be equal. That's one way of thinking about it for the matrix multiplication. Okay, so dash means transpose, by the way. Tf dash means tf transpose. Maybe you have thought of it as, sometimes you people write it as tf transpose. I tend to write it as dash. Okay. So what I mean by this is tf's transpose. Tf itself is the eigenvectors of the matrix tt, where tt is dt dash times dt. Now notice the trick, here is once you start with dt, then everything is just, there is no mnemonics. You don't need to remember what is u supposed to stand for, what is v supposed to stand for, what is m supposed to stand for. Everything is pretty obvious. That's why I want you to think in terms of dt matrix and df and ff and df dash. Okay? That way you will never make any, there's nothing to get confused about. Okay, so this is so of course the eigenvectors of tf are the tt vector. So the tf is the eigenvectors of tt. Now I'm going to put tf dash here. So I get eigenvectors like this. Right? Okay? Now, once again, since this was tt is also a symmetric matrix, you can always compute the eigenvectors of it. Symmetric square matrix. What's interesting about it is, here is the other interesting thing. So these are eigenvectors. The other question is, I took eigenvectors here. What else is left when I do eigendecomposition? Eigenvalues. Where did they go? Well, that's what I'll put here. It turns out that even though tt and dd matrix are different sizes, they'll have the same eigenvalues. And you could sort of think of them as these are the eigenvalues of sort of the correlation matrix. dd is a correlation matrix, document-document correlation matrix. dt is a term-term correlation matrix. Okay, so you can think of these as sort of the eigenvalues of the square of the matrix you are interested in. Okay, so to get this back, what I'll actually put here is I will take square root of lambda 1, square root of lambda 2, etc. Where lambda 1 to lambda k are the eigenvalues of either tt or dd. They'll be the same. So this all looks like magic. This is why actually, I was hoping that I can have MATLAB running here. I don't think it is. But if you have access to any, once you go home, you can actually take any arbitrary matrix and compute the SVD MATLAB, for example, allows you to compute SVD directly. You can also compute it, and then you can check whether the SVD follows these rules. That's one way. Okay. And if you listen to that lecture that I pointed out in the from linear algebra by Gilbert's rank, you'll get an idea as to why actually this would work. Okay. Now, here's the interesting thing. So now I basically have this becomes this times this times this. Okay. So going a little ahead to put this in perspective. Okay. Remember our happy matrix, right? Which is basically the 10 documents and 6 terms matrix. Remember, that's the one we've been looking all the time at, okay? And then it turns out that the first 5 are sort of database, the next 5 are sort of statistics and regression-oriented thing. And we have some intuitions about this data. So that's why it's good to use that data. So now if I were to take this, now I have a TD, the TT matrix is this matrix. Okay, if I enter this matrix and then compute the SVD, I will get these 3 matrices. Okay, and the interesting thing here, of course, is this would be essentially, this matrix is DF matrix. This is the FF. As I said, it's going to be a diagonal matrix. Notice they're only non-diagonal. All the non-diagonal elements are 0. Only the diagonal elements actually have numbers. Okay, and then finally, this is the TF matrix. So this, basically, this matrix is the eigenvectors of dt times dd, dt times dd dash. And these are the eigenvectors of dt dash times dt, which is tt matrix. And these are the square roots of the eigenvalues of either dd or tt.
Why FF is not symmetric?
What?
FF is not...
No, the point is that FF basically, what you show is you only show the ones, you can make it, you can always add 0 zeros to make it a square matrix. The basic idea is, in this particular case, notice the following thing. This is a 10 by 6 matrix. What do you think would be the largest rank it can have? 6. You know, so in fact, if it is really truly full rank, then it will be having at most 6 rank. Okay, so that's why you actually see here that there are, in fact, 6 non-zero eigenvalues. Okay, and I can always add extra 0 columns, and so that basically means those become 0 valued eigenvalues. Okay, here actually it turns out that the maximum rank could be 6, and in fact you had the rank 6. But in some other cases, the maximum rank could be 6, and you may only have rank 3. And how I figure out, once I do SVD, I get a whole bunch of things, one of which is that I know the actual rank of the matrix. The true dimensionality is known now. Because this one has 6, that means it's a 6-dimensional data. If you only have, no, everything else below this is 0, then it will only be a 4-dimensional data. Okay? Right? So now having done this, so that's what I'm writing here. So this is the eigenvectors of dd, and this is the eigenvectors of tt, and these are the positive square roots of the eigenvalues of dd or tt. So in fact, the actual eigenvalue for dd matrix is 77.99 square. Huge number. You just took the square. Now once again, remember that you organize the vectors in such a way that the primary eigenvector comes first, and so primary eigenvalue comes first. Secondary eigenvector, secondary eigenvalue, and so on. This is SVD. Okay? Now, let's think about a couple of things. First of all, this decomposition has, remember these are eigenvectors of some matrix. We just found that's eigenvectors of dd matrix. Now, if I have eigenvectors, then if I take 2 eigenvectors and multiply them, basically take the dot product, what do I get? Yes. Why?
Orthogonal.
Because they have to be orthogonal. Okay, remember we are finding an orthonormal basis for this data. And eigenvectors will always be orthogonal to each other. Okay, so you are taking, so in this particular matrix, all the columns are orthogonal to each other. Now, what happens if I take this df, just think about some properties. If I take df, multiply it by df dash, what do I get? What?
DD.
Say it loud. Identity matrix. Because remember, these are all eigenvectors, these are all unit vectors, right? When you multiply df by df dash, you'll get a matrix where only the diagonal elements would be multiplying a particular eigenvector by itself. Multiplying means dot product. Every non-diagonal element would be the dot product of one eigenvector with another eigenvector, would be a 0. Okay, so in fact, these matrices are called orthonormal matrices. Because if you have an orthonormal matrix, then you multiply it by itself, then you'll get an identity matrix. You will use this at some point of time later on. In fact, when you're doing simplifications, anytime you see df times df dash, that's just identity matrix I. In matrix terminology, I is like having 1. Same thing for tf times tf dash. That too is 1. That too is the identity matrix. Okay? And that just comes because these matrices are the eigenvectors of some matrix. So eigenvectors of any matrix are guaranteed to be orthogonal to each other. Now the other question is, why are these things all nicely positive, real numbers? Imagine all sorts of things that can happen. Remember that these are supposed to be square roots of the eigenvalues. Okay, so if I take an arbitrary square matrix, what are the constraints on the eigenvalues? Do they have to be always positive? Do they all have to be always, so positive and negative is possible. Do they have to be always real? Not even that. Right? So a normal matrix, this is again you are remembering linear algebra. Okay? If you take a normal square matrix and a random square matrix, eigenvalues could actually be complex numbers. And you're taking positive square roots of complex numbers. Wouldn't be a very nice thing to do. You can do it. And of course, first of all, I'm not clear what is the positive square root of a complex number. Okay? But you can take square roots of complex numbers. That's not hard. But here nicely you have all real numbers. Is this just for this data? Is it always going to happen? It's always going to happen. Why? Because these are the eigenvalues of DD matrix or TT matrix. And DD and TT have a special property. They are positive symmetric. And positive symmetric matrices are guaranteed to have positive eigenvalues. You see what I'm saying? So normal eigenvectors may or may not be positive. But eigenvectors of correlation matrices are guaranteed to be positive. So that's why you can be always guaranteed that you can take positive square roots of these positive numbers, and since numbers are can be represented cardinally, so you can be the largest, second largest, third largest, etc. In the worst case, if all the dimensions are equally important, they'll all be of the same value. Now that's interesting. I said something here, which is that the size of these values is somehow proportional to the importance of that particular dimension. And when we say something is important, for us all that matters is what? What? No man, what does it mean? Top dimension. So for example, you guys have dimensions, okay? The length of your hair, the size of your nose, the number of your fingers, the color of your face, these are all dimensions. Which is the most important dimension?
The one that captures the most variance.
What?
The one that captures the most variance.
Exactly. Social Security number actually is the most important one, because we are guaranteed that everybody would be different on that dimension. Shirt color, obviously, it's sort of, there are only so many colors. Okay, fingers, no use at all, unless you have interesting hands, basically all of you have the same. Okay, now here's the interesting thing. Think about the following thing. When I'm talking about the most important dimension right now, I mentioned that the most important dimension is the one that captures the most amount of variance. Now suppose I'm trying to decide who should get A in this class and who should get an F in this class. I just do binary classification. Some people will get A, some get F. Would you rather I just make that decision based on the dimension that happens to be the most important in the sense of previous word? No. Because it turns out that I might have once I, for example, decide when I'm trying to do classification, we'll come back to this later on, when I'm trying to do classification, basically what matters is the dimension that distinguishes the classes the most. Do you see what I'm saying? I mean, if I'm trying to figure out who are Caucasians, who are not Caucasians, then, taking dimensions such as the shirt color have no point. But, maybe color of the skin would be a very good indicator. Color of the skin is not actually the one that puts people in the most variance. In fact, I see a general, only a few shades of gray here in front of me. Okay? And yet, if I'm trying to differentiate between Caucasians and non-Caucasians, the most important dimension to me would be the dimension across which the variance for those two clusters is the maximum. Okay, we'll talk about that later again, but if I don't have a classification task at hand, which I don't right now, then I have to assume that everybody is a unique class by yourself. You are a unique class, you are a unique class, everybody is a unique class. So now I want to look for a dimension that somehow preserves your uniqueness in the maximum possible way. And that would be the variance preserving. So when I say this is the most important one, this is the dimension across which you have the maximum variance preserving. Do you see what I'm saying? Okay. And actually, in fact, since I mentioned this, let's look at this picture. Suppose I have, let's say data like this. That's my data. It just happens to have different colors because this is one cluster. That means this data has one label. Okay, and this data is another label. Okay? Now, which is, if you ignore the labels, which is the dimension that is most important? This one. That's where things are most spread out. But if you care about, what you care about is the label, then the dimension that's more important is actually that. Okay, so LSI does not have any notion of label. It's just basically trying to keep the uniqueness of people, uniqueness of all the data items. Okay, so the importance there essentially means capturing the variance. Now the question then is, this will, if you have this, if I multiply this, by this, I'll get my old matrix back. I can tell you this for sure. Okay, and furthermore, if I were to just multiply this matrix by this matrix, df times ff, it will still be a df matrix. It will be of the size of df matrix. Okay. Now the only difference is here these are all the different axes, and these on the other hand are the importance of the various axes. So when I multiply this by this, I somehow essentially take into account the importance of different dimensions. Okay? So if I do that, I know that's kind of hard to see, but this is a df times ff matrix here. Now, remember that the way I've been saying that the whole point of the factor space is that both the documents and the terms are vectors in the space of these factors. So the factors are the axis, x, y, z axis. Okay? Documents, now each document now needs a new coordinates for how to plot it in this new space. Do you understand what I'm saying? So for example, if I had my original axis is like this, x and y, and I've decided for no good reason, I've decided to do x dash y dash as my new axis, a point which had u, v as its coordinates in the original axis system, right? We'll now have to have this and this as its coordinates. So that if I then plot with respect to this axis, if I plot this point, it will be the same point. Right? So df times ff gives me the coordinates of each of the documents in the factor space. Just as dt gives me the coordinates of each document in the term space, df times ff gives me the coordinates of the document in the factor space. Okay? You got that? And similarly, in fact, if you are interested, although we don't care as much, df times ff will give you the coordinates of the terms in the factor space, because terms are also. So for example, in this case, the unit vector in the x direction is this. This is the point. Now this point in this axis will be, that would be its y dimension, and that would be its x dimension. Do you understand what I'm saying? So this is a point, x-axis is defined by the unit vector in the x direction. Now, so that unit vector happened to be this. This had 1 and 0 as its coordinates. But if you see it from the point of view of these axes, then its coordinates are this part, this is y, and this is x. So this is the x dash and this is the y dash. So here even the terms became vectors. So there's nothing magical. You just change your perspective now. Right? Okay? So up until then everything is fine. Now I want to start reducing dimensionality. Now I want to reduce dimensions. How do I reduce dimensions? As I said, one of the beautiful things is, since all of these are maximally uncorrelated dimensions, if I want to, now I have 6 dimensions. If I want to just get rid of, and only have 3 dimensions, I just want to keep these 3. What do I do then? I just go and make these 3 zeros. And then do whatever I was doing before. Do you see what I'm saying? Okay, so all I do in dimensionality reduction is, if I were to I want to just have 2-dimensional data because I want to draw this in the next picture. Dimensional data, obviously I can only draw 2-dimensional data in a slide, right? So I'm going to remove everything other than these two dimensions. So all I need to do is basically make these all zeros. I just remove them, that means they become zeros. Now notice that even after I did this times this would still be a matrix of size 10 by 6. It will still be a matrix of size 10 by 6. Okay, except that 10 by 6 matrix will only have rank 2. And of all the matrices of rank 2 in this whole wide world, that particular matrix would be the closest to this matrix in terms of aij minus a dash ij square sum over. Okay? That's basically the guarantee we are giving. Okay? Yes. What's the question?
Sorry, actually, I didn't got when you say factor space. Exactly what does that mean?
It's just there's a middle dimension. So I actually decided to become, this is my axis. So now x dash and y dash are my factors. Okay? X dash and y dash are my factors, and every point in the original space is also a point in the new space. It just has different coordinates. Okay, so in the case of fish example, size and whatever is not size is the factor space. Original space is length and width. Okay? These factors are latent. You didn't know what they were until you analyzed the data. And even after you analyze the data, you don't have a name for them most of the time. You don't have a name for them. It just so happens that each of these directions are some linear combination of the old directions. But they don't have any semantics for you. In fact, this turns out to be a problem with LSI in terms of making sense of it for lay users. You say, I reduced your data into 2 dimensions. And they say, which 2 dimensions? I say, I can't tell you. Whereas if I tell you I reduced all your features into 2 features, and you say, which 2 features? I say, hair color and size of the nose, then you feel as if you understood what I just said. That may not be the best way to reduce you. Feature selection makes more sense to people because the original features made sense to them, and you just took a subset of the original features that somehow makes sense to. Okay? Okay? Whereas these are newly defined features now. These are linearly defined features of the original features. And so with that, you essentially will have, they don't have to have any names. Okay, now if I remove this, as I said, I multiply this, and this, I will still get my original matrix, a matrix of the same size of the original matrix, which won't exactly have these numbers. I will show you, in fact, let me show you. Okay, here. This is rank 6 matrix. If I were to just take 2 LSI dimensions, like I showed you, and I multiplied the 3 matrices, I will get this. Just trust me. You can go back and trust and verify. Go back and do it in MATLAB. Okay. So this is the matrix you'll get. Okay. Now and then if you do basically reduce reconstruction around it with 4 LSI dimensions, that means instead of just the top 2, you took the top 4 and only zeroed out the last 2. Then you will get this. Now you can like eyeball it and see, does this look kind of closer to this? Compared to that. Remember that this is the ground truth. This is the original document term matrix. Notice here, this thing became 26. This is actually 24. Closer. This one is 18. This is real one value is 21. This is 20. Closer. It's very clear that if you were to compute the matrix distance between this matrix and this matrix, where the distance is defined by take the corresponding terms, take their difference, square it, add these squares. That's the distance. Okay? It's very clear, obviously, that this is closer to this matrix than this. That's a no-brainer. In fact, the one that's really, really close is the one which keeps all 6 dimensions, which will be this. What's interesting is, when I show you this is a 2-dimensional, this is a matrix of size 10 by 6, happens to have rank 2. You can verify this. But there are infinite number of 10 by 6 matrices with rank 2. Why this? Why this? Because this one, there is actually a proof, which I cannot reproduce. It's not by enumeration, is that this will have the lowest distance to this matrix among all 10 by 6 matrices of rank 2. Among all 10 by 6 matrices of rank 2, this is the best rank 2 matrix. And this is the best rank 4 matrix. And this is the best, of course, rank 6 matrix. And now when you reconstruct the data completely, this is how this data looks like. Okay, so you could say, well, originally, now you say, why is this, if I take 4 dimensions, this is in 24, 20, 10, etc. This is different from this. Is this supposed to be more real than this? Well, sometimes you get a signal, which is a bunch of noise. Okay, all of you have these little, earbuds, right? And so you are listening to, let's say, some source, and it's noisy, and then you have a good tuner, and then it basically reduces the noise. Now you tend to say that the reduced noise signal is actually closer to what was supposed to be the real signal than the signal that was input to you. So some radio station was broadcasting, and then it came to your receiver, it came noisy, and then you did some kind of a filtering, okay, and then you got less noisy signal. And this less noisy signal is different from the input. But you think it's actually correct compared to what it is supposed to be. So the point to remember is this is what you are given as the input. But this could have been the result of that malicious oracle which started from real data and did all sorts of crazy, linear, noisy things. And that's how you got this. So the fact that you are not the same as this could be seen as a feature, not a bug. In fact, that's exactly what you feel. If I say I got this really good high fidelity filter, which keeps the input the same as the output, right? You're getting noisy signal and I'll give you exactly the same noise, no difference. How much will you pay me? Nothing at all. Because you assume that the input is noisy. By the way, this connection to signals is not just a random connection. It turns out, for example, that one way of understanding, one elementary way, and any of you had any background in electrical engineering might remember this, an elementary way to handle dimensionality reduction in signals is to compute its Fourier transform. Okay, so you have a signal of that kind of a form, and you are basically going to, you're going to split it into a sinusoid of that, a unit amplitude sinusoid of this frequency, and a unit amplitude sinusoid of a faster frequency, and unit amplitude sinusoid of even faster frequency, and so on. So omega, 2 omega, u omega, etc. So you essentially are saying this crazy guy is an infinite linear combination of these happy sinusoids. Okay? And noise is always, it turns out, of course, when I have this, then again I need to know which are the important dimensions, which are the unimportant dimensions. For the human ear, it turns out that frequencies way below and way above are useless. There is a medium range of frequencies we get to hear. So what they can do is, oftentimes you do high frequency filtering. When you convert this signal into this Fourier transform, then you essentially, let's say, it's basically it would be, let's say, C1 times sine omega plus C2 times sine 2 omega plus C3 times sine 3 omega and so on, plus C 1000 times sine 1000 omega. I can just say, to heck with this. I'll just make it 0 and reconstruct the signal back. That will lose the noise. That's exactly what filtering is. So all the filtering that you ever heard of, that's dimensionality reduction. Latent semantic indexing is filtering. Our filtering is latent semantic. Latent semantic indexing is a particular type of filtering. It's a linear filtering. So is actually Fourier transforms. The basis functions for Fourier transforms happen to be sinusoids. Okay? The reason we got into this is because I'm trying to say that you should try to think that this is probably the real data. This is just corrupted form of the real data. And I got to the real data by filtering the nonsensical additional noise. And the assumption is the less important, the dimensions in which the variance is less, those are probably noisy dimensions. In the case of sinusoids, the important assumption is very high frequency noise, very high frequency stuff, anyway people can't make too much sense of it. So you can remove it and people will still feel it's less noisy. Okay, so that's basically the full reconstructed matrix. But what we actually care about is not the full reconstructed matrix. We are not going to reconstruct the entire matrix. Okay? Instead, what we really are going to do is I just really want to focus on the DF part. I don't want to reconstruct the matrix. I'll focus on the DF part, and then when I zero these out, what do you think will happen? Those things get zeroed. By zeroing these out, you essentially made the DF to be two-dimensional. Now, how do you say something is two-dimensional? It has zeros in everything other than 2 dimensions. Right? Okay? So it's very simple that when you cut this off, you get to cut off, sorry, when you cut these 4 off, you get to cut off these 4 columns. Or just zero them out. Cut off means make them zeros. Now when I do that, now this is the two-dimensional version of the data in the factor space. It is sort of like, remember in the fish example, in the fish example you had length and width, but then when you convert it into size and whatever is not size, and then if you just take one dimension of those, that would basically just tell you the size of the fish. Right? So each fish will now have a size number, and that is its one-dimensional description. Okay? So here I'm just going to do two-dimensional descriptions. By the way, what happens if I went ahead? I mean, I'm going to do this, and I'm going to show how these documents look in space, etc. Why don't I just reduce all the way to one dimension? What happens if I reduce all the way to one dimension? I mean, what if, in fact, the variance is such that this, let's say this is 177 and this is 24 and so on. In fact, you are worried about variance, right? So the question is, how much variance did I lose here? It turns out that it's the same exact idea as before, except, so you have to take the summation of the eigenvalues you kept divided by the total number of, the full sum of the eigenvalues. Except, remember, what you have here are the square roots. So to get the eigenvalues, you have to actually square them. That's the only thing you have to remember. It's the same idea, except you have square roots of the eigenvalues here. So what I get to do is square the first two divided by the sum of the squares above. That would be the fraction of variance you are keeping. So 1 minus that is the fraction of variance you are losing. So here you lost 7.5%. Okay? Now, if I lost 7.5% this way, so if I just went and, if the numerator is just lambda 1 square divided by lambda 1 square plus lambda 2 square, etc. up to lambda 6 square, it may be instead of 7.5, maybe 13.7%. I may not care. I don't mind losing that much variance. What actually goes wrong? Think about it in the background as to why, what would be a reason why you may not want to do, what would be a reason you may not want to do dimension reduction all the way to one dimension? Okay? What?
You will get the points on that dimension.
So what happens?
All the documents have the
You
same
lose
relevance.
you lose the recon.
It will be
No. So there is a very syntactic reason. You're coming close to it. Remember, we picked a distance as a default. What distance did we pick? Cosine theta. It's not that points on single dimension don't have distances. Of course they do. All your total marks in the end of the semester would be in one dimension, total mark. And here is 98, here is 22, here is 3.
We'll have to use Euclidean distance.
Yes, the point is, if you were to use, so what you should ask me, if you want all of you to get the same grade, either A or an F, you should say, Rao, why don't you use cosine theta distance for deciding our innate worth, but just assume that total marks is the only dimension that matters. Then in the total marks dimension, all of you are one similar. Because in that dimension, the unit vector is just one unit vector. And you're taking cosine theta between that and itself, and it will always be 1. So it's only because you tend to take cosine theta similarity that we never will look at one-dimensional approximations. There's nothing wrong with them. In fact, if you use Euclidean distance, they'll be fine. But for cosine theta, it won't make sense. Okay? Okay, so now I have documents in these 2 dimensions. So this is actually some space where this is the x-coordinate, y-coordinate, x-coordinate, y-coordinate, x-coordinate, y-coordinate. So I can actually draw this, right? It's a 2-dimensional data. I can put an x-axis, y-axis. Notice that all I am getting is these coordinates of the point. The original coordinates are lost now. I'm getting the coordinates in this green space. So when I draw them, what would I do? I'll always put the green like this, and then that would be some point like this. Right? Okay? So if I were to do this, here is the principal component direction 1. This is the component direction 2. Okay? Now, forget about D2 and D1. Just look at all the point numbers here, they correspond to the documents in your original corpus. Okay, now go back and see that first document is minus 30, 11. Second document is minus 30 and 10.7. So they're actually going to be very close to each other as points in this space, right? Okay, so you do see 1 and 2 are next to each other. So I'm just trying to show you that. I didn't cheat. I actually put that data here. What do you see? This is supposed to be, despite all the matrices, etc., this is the time you wake up and say, man, this was worth it. Right? If you didn't, then you essentially got all stuck up with, you know, vectors and matrices and stuff. There is a beauty to this picture. What is the beauty?
This X and Y axis are basically one is correspond to database, other one is static.
Yeah, so it's not X and Y axis. So notice that 1 to 5 are in this line. And 6 to 10 are on that line. So you almost made sure that the cosine theta similarity. So in some sense, even if you were just kind of looking at this data and say, you know, can you do clustering? Cluster this. You know, you would have probably said, yeah, this is one cluster, that's another cluster. Right? And furthermore, when you do your vector similarity, you would have essentially said, these guys are closer to each other than they are to those. Those guys are closer to each other than they are to any of these. Beautiful. You see what I'm saying? It's really worth it. By coming here, we now have seen that all the database guys really are closer to each other than all the statistics guys. I want to tell you one more thing which should really make you even happier. Okay? Which is, suppose I were to give you 2 more documents. Document D1 is a new document containing just 10 occurrences of the word database. Document D2 is a document containing 50 occurrences of the word SQL. Do you think these 2 documents are somehow close to each other? Just forget about the data. Just one is that SQL and one is database. Must be very close. Now suppose you were to compute the dot product between these 2 vectors. What will you get? 0. Right? Because they don't share any dimensions. They do not share any dimensions. So you essentially acted as if database and SQL are independent when they are not independent, given the data. And the reason you can see that they are not independent is because you kind of see that any document which has the word database is likely to have the word SQL. And so they are actually more similar than they think they are. Now the question is, does your LSI know what you know? So if I were to take so remember this is database, so one of the terms is database, T1. So if I take the vector 50, 0, 0, 0, 0, 0 and multiply it, okay, multiply it by this matrix, I'll get 50, 0, 0, 0, 0's coordinates in the new dimensions. Right? Same thing I can do for D2. Okay? Now I can plot D1 and D2 on the same space. And here is D1 and here is D2. I told you that LSI is supposed to capture synonymy, polysemy, and correlation and everything. And there you go, it did, essentially. Right? So you would never have thought that these 2 documents are connected at all. D1 and D2 are not connected because they have not a single dimension common. And yet if you put it in the factor space, they're actually very good relatives.
So in the case of polysemy, it would be dividing instead of putting together, right?
Exactly. Okay? So, and in fact, notice the way the polysemy occurred is the word database was occurring also in the statistics books, and yet they all came off here. And they became separated from the occurrence of database in this meaning. So database is being used in 2 different meanings. One this way, one that way. Now my question is, what is this feature?
is?
You have no clue what this feature is. That was my point I was telling you, right? I converted my data into 2 dimensions. What are those 2 dimensions? I have no clue. They just basically, this just happens to be, this dimension happens to be, so happens to be whatever these vectors are saying, which is a linear combination of the original dimensions. And they don't necessarily have to have a name that you can understand in your domain expertise, given your domain expertise. But it does seem to capture your intuitions in terms of the final answers. That's the beauty. Do you see what I'm saying? So you got the 2 nice different clusters, and you also got these 2 guys being close to each other, which is what your intuition says, which is not what the normal vector similarity would have said. And LSI was able to capture this. This is latent semantic index. That's it. Okay? So now all I'm going to do next is how do you go about doing it as a program? You know, what you do is, given a query, essentially you need to take the document corpus, first convert it to do an SVD on it, so you know that you have the ability to do DF. Okay, so the simplest idea for doing, now notice that I don't really want to, in fact, even if I don't have any query, LSI can be used. So even before these 2 guys came along, and right now I didn't tell you what the query is, you still are very happy. Why? Because you are able to see clusters in the data that you couldn't see before. You see what I'm saying? So in fact, one way LSI is very useful is, you know, we'll talk about this in passing later on, because I've already explained everything here. If you have a bunch of data and you're trying to compute clusters over the data, the best way to, one way to do it is, of course, we'll see that you need to have a distance metric and you need to apply it, you know. But the point is that distance metric in the original space is useless, because, for example, it would have said this is probably closer to that than this. So what I could then do is first reduce the dimensionality of the data, then find clusters in the reduced space. You understand what I'm saying? And that would be a much better clustering approach. So in fact, clustering is connected to dimensional reduction. Things that are similar won't be seen to be similar because of all these additional extraneous details. So you reduce the dimensionality, they start looking very similar. Okay? But we are not interested in clustering right now, although we will be a couple of weeks from now. At that time, remember, this is a great idea, you know, that you can come back to this. So the one other thing, of course, is if I give you a query, what do I do? If I give you a query, I don't necessarily need to compute the document similarity. I need to compute the document query similarity. Except query is a document. Okay? In fact, I would actually say that instead of thinking of D1 is a new document and D2 is a new document, suppose I just say D1 is my query called database. What is it close to? So D1 will come plunk fall here. So if you take cosine theta between D1 and any of these guys, that would be larger than cosine theta between any of these guys and D1. Right? So you did capture that already. Okay. So how did I capture this? I essentially took my query and I took it into the vector space. That's what I did. Okay. So how do I do that? There's an easy way, there's a hard way. Okay. The easy dumb way is take the query, add it to the document corpus, then do the SVD. Then query is already a document. Then just find the similarity between that row and every other row in the reduced space. Dumb idea, because every time you get a query, you change if you compute the SVD. Even if you're really purist, then an additional document does change the variance. And so it does change the axis. But to the extent you believe that the number of original documents is so large that one little query is not going to completely change the latent dimensions, what you want to do is keep these documents as they are, these matrices as they are, just do it for once for the original document corpus, and then essentially multiply the query. So basically, I need to get the query's representation here. And it turns out, I actually kind of I wasn't being completely truthful when I said if you have 50 times database and 0 times everything else, I can get its two-dimensional thing here by just starting with 50, 0, 0, 0 and multiplying it by this. If this wasn't late in the evening and if you're still awake, you would have said, what the heck are you talking about? 50, 0, 0 should be supposed to be here. This is already the DF representation of 50, 0, 0. Okay, and so in fact, the way I said it won't work. In fact, I need to have the DF representation. Okay, in fact, what I really need is DF times FF representation of just the query vector. And it turns out this is where our little math helps. Okay, look at this. dt is df times ff times df dash. Right? Now q. If q were to be part of this decomposition, then there would be a document in the df, a column in the df corresponding to q times ff times df dash. That would be equal to q. What I really want is dfq times ff. Right? That's all I want. What I still have is this df dash. If I multiply both sides by df, right, then q times df is dfq times ff times df dash times df. Df dash times df is I. We said this, right? Because df dash is an orthonormal matrix, df dash times df is an identity matrix. So the easiest way, actually the way you're supposed to get the coordinates for the query is multiply the query by the TF matrix. Okay? So in my example, what I basically did to get D1 and D2's coordinates in this space, what I had to do is D1's, let's say D1's is 50, 0, 0, 0, 0. So I multiply 50, 0, 0, 0, 0 by TF matrix. I would then get what I get would be equal to the dfq times ff. That's exactly what I just showed you. Okay? So all you need is convert the query vector separately to the